For this section, we're going to be talking about solving trigonometric equations. So a trigonometric equation is basically what it sounds like, just a standard equation like x equals 5 or 2x equals 3. But instead of just x, we now have a trig function involved. Something like sine of theta plus 2 equals negative 1. So, with that in mind, let's go ahead and do a quick recall of solving x squared equals 1. How could we go about solving this? Well, remember, there's a variety of ways to solve this problem, but the most common way is just to take the square root of each side of the equation, and when we do, we get x equals plus or minus 1. Notice we have a plus or minus 1, not just 1, meaning there is more than one answer that solves this problem. The same thing is true for trig functions. Remember, if you take 30 degrees and plug it into sine, it will give you the same value as if you took 30 degrees plus 360 degrees, so 390 degrees, and plugged that into sine. So there will be infinite answers typically for these trigonometric equations. With that in mind, let's go ahead and try to solve the following problem. We have the square root of 3 times sine of theta plus 1 equals negative 1/2. And we're solving it such that theta is in the interval 0 to 360 degrees. To start off with, we're going to get sine of theta alone by subtracting 1 from each side of the equation, which gives us the square root of 3 times sine of theta equals negative 1/2 minus 1. That's the same thing as negative 1/2 minus 2 over 2, so we get negative 3 over 2. Remember, if you have trouble with fractions, you can always show that off to the side to make it easier for yourself, but just to save some time. And now from here, we now want to get sine of theta alone, and we can do that one of two ways. We could divide each side by the square root of 3, or very similarly, we could multiply each side by 1 over the square root of 3. And this is the same thing as dividing each side by the square root of 3, but it makes it easier to simplify the fraction on the right side when we multiply them. So the square root of 3 will cancel off, leaving us sine of theta equals negative 3 times 1 is negative 3, over 2 times the square root of 3 is 2 square root 3. And now we'll go ahead and rationalize this by multiplying the top and bottom by the square root of 3, which gives us sine of theta equals the negative square root, negative 3 square root 3. There's a lot of 3's here. Negative 3 square root 3 over 2 times the square root of 3 times the square root of 3 is just 2 times 3. And now notice we have a common 3 in the top and bottom that will cancel out, leaving us with negative square root 3 over 2. So, after all of this, we've now solved for sine of theta, giving us sine of theta equals negative square root 3 over 2. And finally, to solve for theta itself, the variable, we will take sine inverse of each side of the equation, which leaves us with theta equals sine inverse of negative square root 3 over 2. Okay, and now there are a few ways to approach this. We could go through and find what sine inverse of negative square root 3 over 2 is, which would be negative 60 degrees, and then find some reference angles from there, or we can just immediately jump to the reference angles. And the way we can do that is, let's just ignore this negative for a moment. What's sine inverse of the square root of 3 over 2? Well, that's 60 degrees. And now, because we know it was negative, where is sine negative? That's in quadrants 3 and 4. So we need to find the reference angles to the reference angles to 60 degrees in quadrants 3 and 4 to find the solutions to this problem, because those will be the only two values between 0 and 360 degrees that solve the original equation, where sine inverse of negative square root 3 over 2 is equal to theta. So, to find our first reference angle for 60 degrees in quadrant 3, remember, to find that reference angle, we would just take 60 degrees and add 180 degrees to it. We're basically working backwards from our old reference angle methods. So we are adding 180 degrees because we're in quadrant 3, I apologize, which gives us 240 degrees. And now when you're in quadrant 4, typically you would take your angle and subtract it from 360 degrees, and we're still going to do the same thing here. We have 360 degrees, and we will subtract our angle from it, which leaves us with 300 degrees. So theta is equal to 240 degrees as well as 300 degrees. And both of these values are the only two values between 0 degrees and 360 degrees that solve this original equation. Now, this is a very complicated process. It's okay to feel lost here. It's not something you'll just learn instantly, but we're going to be going through several examples of this. So there'll be plenty of time to keep learning it, and then, of course, practice makes perfect. You should try a bunch of problems on your own from there. So the next problem we want to solve is 2 sine of x divided by 2 equals 1, such that x is between 0 and 2 pi, then for all solutions. So this v with a line through it, basically what looks like an upside down capital A, means for all. So to start off with, notice we have x divided by 2 inside of our sine function. That means we have a half angle identity in this problem. But notice that the interval we were given was for x, not for x over 2. So we have to create the new interval off to the side. We know that x is greater than or equal to 0, but less than 2 pi. So to solve for x over 2, we have to divide everything by 2. Which gives us x is greater than or equal to, x over 2 is greater than or equal to 0, but less than pi. Now we can begin solving for x over 2. We'll start by dividing each side by 2 to get sine of x over 2 alone. Just ignore this right here. This was just to make a note earlier. So when we divide each side by 2, we get sine of x divided by 2 equals 1/2. And now to get x over 2 alone, we're going to take sine inverse of each side of the equation. And when we take sine inverse of each side of the equation, we're left with x over 2 equals sine inverse of 1/2. We want to find all the values where this can be possible. So all the angles that plugged into sine give us 1/2, but they also have to be between 0 and pi, because remember, we are solving for x over 2 here. Not just x, but the interval for x over 2. So the first value, the first angle where sine can equal 1/2 is pi over 6. That's in quadrant 1, where sine is positive, and this is a positive 1/2. Now we have to check, is there another value between 0 and pi that gives us a positive 1/2 for sine? And there is, because sine is positive in quadrants 1 and 2. Oh, that's a terrible 0. So because sine is positive, and I should really make that an E, because sine is positive in quadrants 1 and 2, we need to find the second angle where sine can equal positive 1/2. And basically, one really nice thing about working with radians is when you're finding a reference angle in another quadrant, it's going to have the same denominator. So what value has a denominator of 6 in quadrant 2? And it's one of our memorized angles. Well, that's 5 pi over 6. If that method doesn't work for you, then remember to find your reference angle in quadrant 2. All you would have to do is find pi minus pi over 6. And that would still give you the 5 pi over 6. So whichever one you find easier. And these are the only two values between 0 and pi that solve the original equation. So now that we have them, we don't need to just solve for x over 2 anymore. Now we solve for the original x value that we were looking for by multiplying each side of the equation by 2, which gives us x equals pi over 6 times 2 is 2 pi over 6, or pi over 3. And 5 pi over 6 times 2 is 10 pi over 6, or 5 pi over 3. So these are the two solutions between 0 and 2 pi that solve 2 sine of x divided by 2 equals 1. But now we want to solve for all solutions. And the way we do that is remembering how to find the period of our trig function. Remember, the period for sine or cosine is 2 pi divided by b, where b is the number multiplied to the variable in our trig function. In this case, the variable x is being divided by 2. That means it's being multiplied by 1/2. So simplifying this, we get 2 pi, and instead of divided by 1/2, we'll change it to multiplied by 2 over 1. So we get 2 pi times 2 is 4 pi. The period of this problem is 4 pi. So every time we travel a distance of 4 pi, we get the same answers. So how would we say that for all solutions? Well, we'd say x equals pi over 3 plus 4 pi times some value n, and x equals 5 pi over 3 plus 4 pi times some value n, such that n is in the integers. Remember that symbol that looks like a double Z represents the integers. It means all whole numbers that are positive or negative. So anytime you multiply 4 pi by a whole number, whether it's positive or negative, so anytime you multiply it by an integer, so something like 2, 0, negative 7, 2015, anything like that, and then you add that value to pi over 3 or 5 pi over 3, that will be another solution to this original problem, 2 sine of x divided by 2 equals 1. So we've now found all solutions to that equation. From here, I want you to take a moment, see if you can't solve 4 sine of alpha cosine of alpha equals the square root of 3 such that alpha is between 0 and 360 degrees, then for all solutions. And you will need an identity for this problem. That's just a little hint to solve it. Okay, so going through this, the first thing that you hopefully noticed was we have sine of alpha times cosine of alpha. Whenever you have 2 times sine of alpha times cosine of alpha, that's the double angle identity for sine. So I'll write that off to the side. 2 sine alpha cosine alpha is equal to sine of 2 alpha. So now that we have that, notice in this problem we have 4 instead of 2. So if we were to divide each side of the equation by a 2, that would give us 2 sine alpha times cosine alpha equals the square root of 3 over 2. And now from here we can apply our double angle identity. So the left side will become sine of 2 alpha equals the square root of 3 over 2. And now before we begin solving from there, we need to recreate our new interval. This interval is for alpha, but we need it to be for 2 alpha. So taking 0 degrees is less than or equal to alpha, which is less than 360 degrees. If we multiply everything by 2, we'll get 0 degrees is less than or equal to 2 alpha, which is less than 720 degrees. So this is the interval that we're solving for 2 alpha. And now at this point, we can take sine inverse of each side of the equation, which gives us 2 alpha equals sine inverse of the square root of 3 over 2. We want every value that when we plug it into sine, we get a positive square root 3 over 2. And all of those values have to be between 0 and 720. So the first value where that's true is in quadrant 1, that's 60 degrees. The second value where that's true is in quadrant 2. The reference angle to 60 degrees in quadrant 2 can be found by taking 180 degrees and subtracting 60 degrees from it, which gives us 120 degrees. Now there aren't any more values in quadrants 3 or 4 where this can be a positive square root 3 over 2. It can be negative, but that's not what we're looking for. But there are more values that come before 720 degrees where this will be a positive square root 3 over 2. And we can find them by just adding got a little ahead of myself, adding 360 degrees to each of these angles. Once we make a complete rotation, we'll be back to the same angle value when we plug it into sine. So 60 degrees plus 360 gives us 420 degrees, and 120 degrees plus 360 gives us 480 degrees. And we'll show the work off to the side just very quickly. And now that we have all of the angles between 0 and 720 that solve sine inverse of square root 3 over 2, we can now solve for alpha itself, not just 2 alpha. So we'll divide everything by 2, which gives us alpha equals 30 degrees, 60 degrees, 210 degrees, and 240 degrees. All of these values are in the interval 0 to 360 that we originally needed for alpha, and they all solve this original problem for sine alpha, cosine alpha equals the square root of 3. But now we want to solve for all solutions. And the way we're going to do that is going back to this step where we had sine of 2 alpha equals the square root of 3 over 2, finding the period at that part of the problem, because we can't really find it up here since we have two separate trig equations. So finding it here, we have p equals 2 pi over b. Well, b in this case is the number multiplied to alpha, which is 2. So the period is just pi, or 180 degrees. So every time we add 180 degrees to any of these four answers, we get another solution to the problem. And if we subtract 180, that will also be true. So what's our for all solutions answer? Well, we have 30 degrees plus 180 degrees times n. We have 60 degrees plus 180 degrees times n. And now notice these two other values, we don't need to write the plus 180n for either of them. In fact, we don't even need to include them because they are already included in these two answers. 30 degrees plus 180 degrees gives us 210 degrees. And 60 degrees plus 180 degrees gives us 240 degrees. So writing 210 degrees plus 180 degrees n would just be rewriting this solution, which we don't need to do. So we can ignore these two since they already come up in these two values, and we can say such that n is in the integers. And this is our for all solutions answer. Okay, so from here, again, I'd like you to take a moment, pause the video, see if you can't solve for cosine squared x minus sine squared x minus 1 equals 1. And again, you are going to need another identity here. In this case, you're only solving it such that x is between 0 and 2 pi, not for all solutions. Okay, so trying this together, hopefully the first thing you noticed here was cosine squared x minus sine squared x is equal to cosine of 2x. That's one of our double angle identities for cosine. So we get 4 cosine 2x minus 1 equals 1. And now before we begin solving for 2x, we need to set our new interval because our interval right now is just for x. So right now we have x is greater than or equal to 0, but less than 2 pi. To find 2x, we're going to multiply everything by 2, which gives us 0 is less than or equal to 2x, which is less than 4 pi. And now we can begin solving for 2x. Oh, and I wrote 2 pi. Sorry, 2x. Now we can begin solving for 2x. So we start by adding 1 to each side. which gives us 4 cosine of 2x equals 2. We'll then divide each side by 4, which gives us cosine of 2x equals 1/2. And then we can finally take cosine inverse of each side of the equation, like so. Which gives us 2x equals cosine inverse of 1/2. So we want to find everywhere that cosine has an angle that when you plug it in, it gives you a positive 1/2. Well, this is a little trickier than the sine functions we've dealt with. For cosine, remember cosine is positive in quadrant 1 and quadrant 4. So, quadrant 1 is the easy one. What angle in quadrant 1 gives us 1/2 in cosine? That's pi over 3. But now we need the angle in quadrant 4 that gives us a positive 1/2 for cosine. Because remember, in quadrant 2 and 3, it will give us a negative cosine value. So in quadrant 4, to find the reference angle of pi over 3, we can do it one of two ways. We can say what angle in quadrant 4 has a denominator of 3 that we memorize. That would be 5 pi over 3. Or we can find the reference angle by finding 2 pi minus the pi over 3 that we already had, which again gives us 5 pi over 3. But we're not done from there, because remember, we're solving for 2x being between 0 and 4 pi. This is just between 0 and 2 pi. So if we add 2 pi to each of our angles, pi over 3 plus 2 pi is the same thing as pi over 3 plus 6 pi over 3. That gives us 7 pi over 3. And 5 pi over 3 plus 2 pi is the same thing as 5 pi over 3 plus 6 pi over 3 if you found a common denominator by putting 2 pi over 1 and multiplying the top and bottom by 3, just to show what's going on in this last step. And when we combine those together, we get 11 pi over 3. These are all the values between 0 and 4 pi that solve 2x. So now we can finally solve for x by dividing everything by 2. And saying divide everything by 2 is the same thing as saying multiply all the denominators by 2, which gives us pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And that's our solution, since in this case we did not need to solve for all solutions.